Hi, my name is Leah Kiner, and I'm going to be presenting the work from the 2025 AAS GNC conference titled Two-Axis Gimbal Simulation Overview for the Emirates Mission to the Asteroid Belt. And I'd like to thank my co-authors, Dr. Cody Allard, the GNC lead for the EMA mission at the Laboratory for Atmospheric and Space Physics, and my advisor, Dr. Hans-Peter Schaub. So first, an overview of the EMA mission. The Emirates mission to the asteroid belt is the first main belt multi-asteroid tour mission. The Explorer is named the Mohammed bin Rashid Explorer, and its launch is planned for 2028. The Explorer will fly by 6 asteroids and rendezvous with the 7th, named Justicia, in October of 2034. And the focus of this work is the 2 solar electric propulsion subthrusters, which are used to traverse the solar system during the EMA GNC setpoint state. And I'd like to point out that my colleague, Dr. Ricardo Colon, presented last year at this conference. He presented the guidance algorithms that he worked to develop for this EMA GNC setpoint state. And so I'm not going to be going into those algorithms in this presentation. Instead, I'm going to be talking about the simulation and control of the 2-axis gimbal platforms that these SEP thrusters are mounted on. However, for context, here are some highlights of this set point state. The SEP thrusters are used to thrust along an inertial reference direction, while the Explorer's solar arrays are kept pointed at the sun. And the set point is responsible for the management of the momentum of the spacecraft due to external perturbations, such as SRP, while also absorbing the accumulated momentum along the thrust axis by the reaction wheels due to the thruster swirl torque. So next, I will give an overview of these 2-axis gimbals. So specifically, a 2-axis 2 degree of freedom gimbal platform is what actuates each EMA SEP thruster. The thrust direction vector t-hat is defined as the third gimbal body frame axis G3, which points in the direction of the thrust force felt by the spacecraft, which is opposite to the ejection of particles from the thruster. And so there are 3 important reference frames for this problem setup. First, we have the spacecraft body frame B, and we can see that here, it's fixed to the rigid spacecraft hub in gray. And then we also have the mount frames of the gimbals M, which the gimbals actuate relative to, and these are fixed to the hub. And then we have the gimbal body frames G. So in this figure, this rightmost figure, we can see that the G frame is what's attached to the gimbals, which actuate with the gimbals relative to this hub fixed mount frame. And then in this overhead view and the side view, we can see the attitude of the mount frames of the gimbals relative to the spacecraft hub. In the overhead view, we are looking down from at the bottom of our EMA hub from the B3 axis at the gimbals. And then in the side view, we are looking at the B1 axis at the gimbals, and we can see that they're canted about 15 degrees about that B1 axis. And so later I'll be going into more details about how these gimbals actuate. So first, we use a tip-tilt 1-2 Euler angle sequence to model the attitude of each gimbal relative to those hub fixed mount frames. So just to be more specific, we first tip about this angle psi, about the gimbal mount frame first axis, and then we perform a second axis rotation about the G2 axis by this angle phi, which is that tilt angle. And so in this bottom, we see that the gimbal attitude direction cosine matrix relative to the mount frame is this matrix here. And so next, the tip-tilt motion of each gimbal is controlled by 2 1-degree of freedom stepper motors. And what's important to note here is that for this mission, in order to resolve the attitude of each gimbal, we only have the knowledge of the current step counts or the positions of these stepper motors. And so the stepper motors can be commanded individually or simultaneously to actuate the gimbal thrust axis through its allowable range of motion. And so each motor actuates within a specified range, so they don't have a full 360-degree allowable range of motion. They have an upper limit, which is a hard stop rotational limit. And then finally, rather than modeling the electrical dynamics of these motors, we are instead modeling a bang-bang acceleration profile for the acceleration of each motor. And so this is just an example here where we're only actuating motor one. And so that bang-bang acceleration profile is seen in that bottom of the three figures. And then the corresponding motor rate and angle are in those plots above. So next, the boundary of the gimbal is specifically produced by actuating each motor individually to their hard stop limit. So essentially, this traces that outer boundary of the gimbal motion. So if we start where both motor angles are 0 in the stowed configuration of the gimbal seen by the star in this figure, if we actuate motor 1 to its hard stop limit, we trace the northeastern edge of the diamond. And then if we actuate motor 2 to its hard stop limit, we trace that northwestern edge of the diamond. So anytime we actuate one of the motors independently, we run the gimbal actuates parallel to one of the edges of the diamond. Whereas when we actuate the motors together, the gimbal traces an east to westward path. So if we only actuate motor one, then the gimbal moves along a path that is parallel to the northeastern and southwestern edges of the diamond. And if we actuate motor two only, then the gimbal traces a path that is parallel to either the northwestern and southeastern edges. Um, and when both gimbal angles are 0, that denotes the home position which is at the center of this boundary, which is where the gimbal is during the majority of its actuation over the course of the mission. And then we're just looking down at the gimbal, so the thrust axis is pointed out of the page for this example. And so next I'll be presenting the algorithms that we developed here. So there's quite a few. The first algorithm is an axis to gimbal angles algorithm that just simply takes the commanded thrust direction in body frame components and maps it to the reference gimbal angles to achieve that attitude. And after that, we feed those reference angles into the second gimbal angles to motor angles module, and we use interpolation to obtain the required motor angles. And the way that we interpolate is we use these gimbal to motor tables, and we have one for each motor, where the gimbal angles are implicitly along the rows and columns of these tables, and they are discretely spaced by a fixed angular amount. And so if both of these reference angles fall along a row and column of the table, then we don't need to interpolate. We can simply pull out the corresponding motor angle. If only one of the reference angles falls along a row or column, then we use linear interpolation. And if both of the angles do not fall along a row or column, then we use bilinear interpolation, and we have to pull out the upper and lower bounds for each of the gimbal angles, which results in 4 different bounding angles for each motor. And then we use bilinear interpolation to obtain the corresponding motor angle for each motor. And there is a little bit more to this algorithm that I talk about in the paper. But to summarize this as clearly as possible to make this module as general as possible, we need to account for cases where the range of both of the gimbal angles are not identical. And this results in blank entries in these tables where if you request those angles, then you would extract invalid motor angles that would be blank. So in order to prevent this, we do a boundary case check after we extract all of those bounding values from the table. And then we have to adjust the type of interpolation that we do if some of the motor angles are invalid. And next we have two instances of the stepper motor controller module where the inputs are those reference motor angles that we obtained, and the output is an integer number of motor steps that drives us as close as we can from the current motor angle that is stored in these modules to that incoming reference motor angle. And then these motor step commands are sent to these blue stepper motor modules. Again, we have one for each stepper motor. And these modules simulate the bang bang acceleration profiles for each step of the motor actuation. And they simulate the full stepping motion of each motor for this commanded number of steps. And so they output the motor angle, rate, and acceleration in time throughout the entire actuation of the motors. And once the motors complete the actuation, they continue to output the current motor states. And so here's a flow diagram for this algorithm that is described more in the paper as well. And then the bulk of the work that was done in this paper was actually in developing this two-axis gimbal module because there's actually quite a bit that this module has to deal with depending on the motor step commands. For example, the motors can be commanded individually. They can be commanded together with the same number of steps. They can have opposite number of steps where one motor is commanded to move forwards while the other one is commanded to move backwards. And they can also be commanded to have a unequal number of steps. So this module essentially needs to handle all those different types of cases. And this module outputs the current gimbal tip and tilt angles in time, and it also outputs the attitude of the gimbal as an MRP, the angular velocity, and the angular acceleration of the gimbal, all relative to that hub fixed mount frame. And so specifically, there are two different ways that the gimbal will actuate depending on the incoming motor step commands. If the absolute value of the motor step commands match, then the gimbal actuates in one segment while the motors are also actuating. And so the gimbal takes the same number of steps as the motors are taking. And we essentially determine the required PRV, the principal rotation vector angle that the gimbal will need to rotate through with additional motor to gimbal angle tables as seen in this bottom right-hand figure. And so once we've resolved the PRV angle that the gimbal needs to move through, we determine the step angle for each gimbal step. So the gimbal completes one step at the same time as the motors are completing a step. And we obtain that step angle by dividing the obtained PRV angle by the number of steps that the gimbal is actuating. And so the step time for the motors and the gimbal are identical in this case. And then that's how we back out the required bang bang acceleration for the gimbal. And then if the motor step commands do not match, then we have two actuation segments where that first actuation segment is what I just discussed, but the second segment, the motor with the remaining steps needs to finish its actuation. And so the gimbal will then move the same number of steps as that motor with the larger number of steps. And so that algorithm flow is shown here, and more details are also provided in the paper. And so finally, that last module, I actually presented this work 2 years ago at the ASGNC conference, where we developed a prescribed motion state effector module that provides the contributions of any prescribed motion component back to the overall spacecraft equations of motion. And so here are those equations of motion. We have the translational and rotational equations of motion for a rigid spacecraft hub with a connected prescribed motion component. And what that means is we can essentially feed the gimbal states in time into the right-hand side of these equations of motion. And then this module essentially provides all of those contributions, the mass properties, and the right-hand side of these equations back into the overall spacecraft equations of motion in order to simulate the contribution of the gimbal motion to the dynamics of the spacecraft. And so finally, for the simulation results, first we have a general commanding scenario for the gimbal where we start in the stowed configuration in this right-hand plot, and we desire to actuate the gimbal to a tip angle of -5 along the x-axis, and then a tilt angle of -10 along the y-axis in red. And we can see that both of the motors actuate together while the gimbal moves westward. And then we see only actuation of motor 2 while it completes those remaining number of steps. So in this case, the gimbal has 2 actuation segments. And so here this is just showing the motor angles and the motor step counts in time, where we can see that both motors share about 12,000 steps, and then motor 2 has to take a few thousand remaining steps to complete its actuation, which aligns with the gimbal motion that we saw in the previous slide. And finally, we simulated the EMA set point state, where we simulated a 7-day period where we first actuate SEP thruster 1 for the first half of the simulation every hour, once every hour, and then we switch to SEP thruster 2 for the second half. And we can see that the thrust direction error for both thrusters decreases towards 0 and remains close to 0 while each of the thrusters is in operation. And we can see that the reaction wheel speed plot on the right-hand side, the reaction wheels do not saturate after the initial slew to the requested attitude. The reaction wheels start to speed up due to the swirl torque of the SEP thruster. However, after we switch SEP thrusters and after that slew, the reaction wheel speeds begin to slow down due to the opposite polarity of the thrusters. So the reaction wheel speeds return to low values similar to how we started, and we can see that the reaction wheel speeds are able um, to accommodate the swirl torque of the thrusters. So finally, in conclusion, the Emirates mission to the asteroid belt requires independent actuation of 2 two-axis gimbal platforms during the GNC set point state in order to orient the SEP thrusters to a commanded inertial thrust direction. This paper outlines the C++ algorithms developed to command and actuate the SEP gimbal platforms, and the simulation results demonstrate successful execution of the EMA GNC set point state. And future work involves rigorous verification and validation of the algorithms that are presented in this work. And a significant portion of the code for these algorithms are available online at the LASP GitHub. And lastly, thank you. If you have any questions, please feel free to reach out to me or either of my co-authors. Thank you.